Hey guys, it's Mr. Sheeline here. This is going to be the video for the Unit 5.1 lecture notes covering forces. So what we're going to be doing in these notes is pretty much just kind of walk through what a force is, where we see them, and then really focus in on just two of them, two that we're really going to be practicing and looking at, which is going to be gravity and gravitational forces and friction forces. Okay, so the objectives for this particular set of notes is this. Now, I'll talk about this after I've gone through the objectives. So I want you to be able to identify and also define a number of different forces. So pretty much just at least two, which is, again, gravity and friction. There's going to be some others we're going to mention that we'll kind of look at more in the next section of this unit. I also want you to be able to identify friction as a force and differentiate between two different types of friction. And then I want you to be able to calculate mass, to be able to calculate acceleration due to gravity, and also the gravitational force of an object, which is just its weight. So these are the things that I want you to be able to say that I can do at the end of this unit section. Okay, so just to let you know, so I was in a rush to make these notes, and I realized that as I was printing them, that I didn't give you the student version. I basically gave everybody the teacher version, so there's nothing to fill in other than the check your understanding. So that doesn't mean that I want you just to read through these or just gloss through them. Still, you should be going through this video, I'll be adding a bit more context to certain ideas. I'll be circling, telling you this is like an important idea, that sort of thing, throughout the notes. So just to let you know on that. Okay, so this is kind of just an opener. So what is a force? And I want you to really answer that for yourself. In your own words, tell me, what is a force? And then even maybe tie that into an example of where you think you see a force at. So tell me again, what is a force? And then provide an example in these notes here. So just take a quick little second. Tell me in your own words what a force is, and then list an example of where you would see a force. Okay, so just take a second to do that. I'm going to continue though. Anyway, so again, answer that question honestly and put it in your own words to help you kind of see where you're at and where we're going to go from there. So more or less, what is a force? Super simple idea is that a force is just a push or a pull. Now, just so you know, though, yeah, it's a push or a pull. That may seem obvious in some senses, but sometimes it's not so obvious. Sometimes things are happening that you don't even know are happening. There's forces that are occurring where you don't know they're occurring. So a good example of this would be like the floor exerting a normal force, specifically. It's exerting a force back onto you against the force that's pulling you down. Okay. There's the force of an atmosphere pushing against your body. That's just gravity. That's gravity is a force that's pulling you towards the center of the earth. Okay, which I guess now looking at it, I've got all three of these. They're not all three the same, but the last two are pretty much the same. So those are examples though where you would see where there is a force. And when you stop and think about it, yeah, 100% there's a force, but maybe it's something that you don't really stop and think about, so it's not obvious. So they're everywhere that forces are seen everywhere. We encounter them every day, and we're going to try to maybe identify some, know how to calculate some, and all that good stuff. So right down here is I would say like the technical. This is the technical definition of force. Now, for the most part, you can just simply say that, yeah, it's a push or a pull. But a bit more technically speaking, a force is some sort of push or pull that makes an object change its position, or a force is something that allows it to stay in a particular position. Okay, that's what a force is, a bit more technically. And we should recognize that and remember a little bit, or at least that should be like, oh, you should be like, oh yeah. That's what we saw in the video the other day, from the crash course video. Okay. Now, multiple forces can be applied to an object all at the same time. However, a lot of these forces can be in different directions. And we kind of get into that in here when we get to what's called a free body diagram. But that's later on in the unit when we get to that. But we call, when we want to identify like forces, happening to a particular object, we would talk about something called the net force. And what the net force is that it's the sum of all forces acting on an object. Okay. Now, it's net is used in the way of like, if any of you guys have taken consumer ed or any little bit about the word net, it's usually attributed with something that's another word called gross. So there's like gross taxes versus net taxes. So gross would be, well, here are your taxes before X, Y, and Z. Net taxes, I say taxes, I mean income, sorry. So you have net income and gross income. So income just meaning how much money you make from your job. So gross income is how much income you make, how much money you make before it's taxed, and also before expenses. And then net income is pretty much what you have left over after you've subtracted your taxes and also your expenses. So the same thing is basically that word net is used exactly the same here, that it's net force. It's the force you're left with that shows or after you've subtracted anything or added anything together in a particular system. And we'll kind of look at what that means later on. But all you need to know for the most part is that the net force is the sum of all forces acting on an object. Okay. So forces are measured in SI units called newtons. So this is something that you were just thrown into in that little engagement thing that we did the other day. But we use the term or the units newtons. We don't need to know what the derived units are for that. Just know that we just measure them in newtons, and we use the letter N in order to denote newtons. Okay, now, not only do we use newtons, we have to remember we have to know that forces are vector quantities. So we super duper care about the direction in which they're moving. Okay, and we'll see why. So let's take a look here, and let's take a look at this as an example of what it looks like, what the net force would look like. So these little arrows down here are what we call vectors. Okay, and that's partially why what this is. These are vectors. Force is a vector quantity, so it makes just sense. It's basically a magnitude of a particular thing drawn in like the form of an arrow, basically. So that's what that is. Anyway, so the image below shows students pushing a box in the same direction. We would then add these forces together to calculate the net force. So this is an example of where you would add in two forces, and we're adding them because they're moving in the same direction to equal out whatever our net force is. So in this case, this is pretty much just what it would look like equation-wise, is that here's the amount of force that one person is putting into the system. Here is the other force, which it looks about to be the same, that the other person's putting in. You add those two together, and this is the net force. This is the overall force of this whole system. Okay, so here and what's important is that both of these people are moving in the same direction. But if we had an example where they were not moving in the same direction, if we had two people pushing with unequal force in opposite directions, we would have to subtract. So hopefully what you're seeing here is that we're actually treating this very much how we treated displacement, okay, which is exactly right. We are treating this as if we're treating displacement. Only difference is it's not so much that we care about where we start and where we end. In this case, it's I guess in a way you could think of it that way, but it's a little bit different in the sense that we're not, these two things are happening at the same time. Like these two are happening at the same time versus displacement where you're like moving this way, stopping, turning around, and then like going here. Okay. But anyway, we're sort of kind of treating it very much the same as displacement. And we'll practice what that looks like in the future. Okay. So students in this image are pushing in opposite directions. The direction of the net force is the same direction of the greater force. Okay. Therefore, the student who pushes harder causes the box to move in the direction that in the direction of that push. So this lady right here is pushing with a greater force than this lady, and so the net force is going to be greater in the direction that this lady is pushing it. So our net force would be this direction with however many newtons, however many newtons it's using up. Okay, or I should say that's left over. Now, it is possible where you can have a zero net force. So in this case, we've got two students who are pushing with the same size of force, but in opposite directions. And in here, we would have a net force on the box of 0, okay, because the two forces cancel each other out. So you can apply a force. Or number of forces to an object and not have it move. It's very possible. A good example is if you go up to a wall, and if you push on a wall, if the wall's not moving over, it's because the wall is pushing back with an equal amount of force. So your net force is 0. The same as like when you're standing on the ground. So gravity is pulling you down, pushing you down against the ground. Well, the ground is pushing back with an equal amount of force on your body, and thus, for the most part, you're not moving. You're not falling through the ground. The ground isn't giving because it can't hold that normal force, that upward force against gravity. So again, these are all examples of where we would see a net force being 0. Okay, so recap real quick. When we talk about net force, when we have two things moving in the same direction, we add them, we add them together, and we would say the net force is moving in this direction. We added them together. Here is where they move in opposite directions, but we've got one individual who's pushing with a greater force, and so we would subtract these because they are moving in two different directions. So our net force would be smaller than so if you notice, and that's something you should notice, is that the net force here is smaller in relationship to this lady's force. It's because we subtracted this lady's force from this right here, and we're left with this, okay? And so the same thing somewhat applies to this guy, that we've got equal amounts of forces moving past one another, but they're in opposite directions. So like this one would be positive, this one would be negative. They cancel each other out, and then you're left with a net force of 0. Okay. Now here are all kinds of different forces that we interact with every day. But again, we're only going to really focus in on friction and gravitational force. But these are other forces that we look at. So there's applied force. So applied force is just like and I would write this down, by the way, in your notes here. An applied force is a force that's put into a system, like pushing a box. It is where an exterior force is trying to propel another thing to change its position. Okay. Then we have friction force. We'll get to that in just a second. We have gravitational force, which again, we'll get to that in a second. The normal force. So again, this is the normal force. So if we've got an object here, and the object has a force due to gravity moving downwards, normal force is just the opposite. It's this guy right here. This is what it looks like. So we've got a box sitting here on the ground. Gravity's pulling it down this direction. The normal force is the ground pushing up on the box with an equal amount of force against gravity. Okay. And then we have what's called the tension force. Tension forces we don't get into pretty much at all. But if you've got let's say you've got like a ceiling here, and let's not do that. You have a ceiling here, and you've got something hanging from that ceiling. Let's say a light. Okay. So what the tension force is the tension force is the force that is, again, opposite of gravity that's being applied to this rope. Okay, so gravity is going to move this way. Tension force moves this way. It's basically just the normal force of hanging objects, really. And then there's drag. Drag is just air resistance. We'll talk about it, and there's some like things that we'll kind of practice a little bit just to kind of recognize what it is. But for the most part, in calculations, we ignore it. Okay, especially when we get to free fall, we just ignore it. Now, okay, so what is friction? So let's just try to think about this in an example. So suppose that you give a skateboard a push with your hand, okay? You've let it go, and you notice, and what you should notice is that the skateboard eventually is going to slow down and come to a stop, okay? So because we go from, your skateboard is slowing down, um, there must be something that's acting on that skateboard to slow it down. There's something that is stopping it. And what that is it is a force, and that force is friction. Okay. It's no different from what you try if you play basketball. If you're running, okay, if you're running and you start or if you start sliding, that's bad business. You don't want to slide. You want to stop right on point. But if you do slide, you still have friction that's being applied to your shoes on the ground in order to stop you. So friction is just the force that opposes a sliding motion of two surfaces that are touching each other. That's really the technical term of what friction is. Okay. It's again the force that opposes the sliding motion of two surfaces that are touching each other. Now, the amount of friction between two surfaces does depend upon what surfaces are in contact with one another. So, smooth surfaces are just smoother. They don't have as many like little what are called microscopic welds. They don't or micro welds. Sorry, they don't have as many of those. They don't have like little teeth microscopically or as much, or they're smaller than say something like an eraser. Eraser has a lot of micro welds, and they're very big, and because that's just rubber in general. Is that rubber and things like rubber have giant micro welds that just keep things from moving and sliding past one another. So friction is caused by micro welds that form between two surfaces. So as shown, a larger force pushing two surfaces together will cause more bumps to come into contact. Okay. Again, this is what's happening at a microscopic level. Okay, at a microscopic level. So that's what we're seeing here in these two pictures. Microscopic level of where you've got reasonable amount of force. So here you have, we would have friction. Here we put in more force, and we have even more friction, which is going to cause more contact right here, which is going to make it harder for us to move things or to get them into motion. So speaking of getting things into motion, we have to know that there are two kinds. Really, there's more than two kinds, but we're going to focus in on two kinds of friction. There's static friction. There's static friction and kinetic friction. Okay, and it's these two kinds of frictions are two kinds of frictions that we've actually should have seen before. If you've ever moved a couch, if you've ever moved like a refrigerator or a stove, or just anything super duper heavy, you've seen the difference between static and kinetic friction. So static friction is just the friction that prevents two surfaces from sliding past one another. Okay. So that would be anything that keeps something from moving, really. It's a friction that keeps everything standing still. Okay. So it's due to the microwelds that form between two surfaces. So you sitting in whatever seat you're sitting in right now, what's allowing you to sit there and not making you slip and slide everywhere is static friction. It's just an amount of force that is needed to be overcome in order to move something. So it's again the friction that keeps you in your seat. It's what allows you to stand in one spot without sliding, and it's what keeps whatever table you're at, there. Okay, that's static friction. And what's important is and easy to remember is that static. If you guys know what static means, it means just no change. Okay, static means no change. So here, so static means like no change. Okay, a good way to remember the difference between static and kinetic. Okay, now we've talked about things that are kinetic before. This would have been before we went on winter break. Kinetic friction, that's the friction that opposes the motion of two surfaces sliding past one another. So it's the friction that immediately begins, that is immediately applied to something that goes from not moving to moving. Okay. So as an example, it's the friction opposing you while you're moving a fridge, while it's sliding on the floor. It's the friction between the floor and a couch when you're moving the couch. Okay. Now, we should be able to know the difference between kinetic friction and static friction much more easily, in the idea that static friction means that there's no change. It means that it's the friction of something, or a friction that holds something in a particular spot. Kinetic friction is the friction of a moving object. So kinetic means motion. Okay? Kinetic means motion. That's the definition of kinetic. It's just motion. Okay? Kinetic energy. It's the energy of a moving thing. Okay? We are studying kinetics, which is the study of just moving things. So kinetic is moving. So if kinetic friction means just the friction on a moving object. Okay. Now, quick question though. Now think about this scenario, because it's an important way to know the difference between these two as well. Now, does it take a greater amount of force to start a heavy object like a couch or a fridge to move? So does it take more force to move a heavy object, or does it take more energy, or does it take a higher amount of force in order to keep it moving? So another way to ask this question, what's more difficult, to get something started or to continually make something move? Think about it for a second. Okay. So what you should have said is that, oh, for sure, like any heavy thing that I've tried to move, the greater force, 100%, the greater force is on, it's on here. It's just to move it, just to start it moving. Okay. Just to get something moving, it takes a whole lot more force and a whole lot more energy than it does to keep it moving. Okay. And again, that's exactly right. That's what we should see. And the reason for that is because our static friction force, is always greater than our kinetic friction force. Always. So again, static friction is greater than kinetic friction. Okay? It takes a whole lot more energy in order to get something moving than it does to keep something moving. Definitely something to remember, and definitely write this down. Okay? Because that's going to be something I'm going to be asking you guys throughout this unit. It's, again, just a way to understand the differences between kinetic and static friction. So check your understanding, number one. Now, I'll also let you know that all the check your understandings are going to be in a separate video. So go ahead and answer this one. I'm going to move ahead. And number two, I'm going to move ahead straight to gravity so that you can go watch those after we've gone through we've gone through the notes here. Okay, so what is gravity? So gravity is an attractive force between any two objects that depends on the masses of the objects and the distances between them. So the force of gravity between any two objects can be calculated if their masses and the distances between them are known. Okay, now that's what's called universal law of gravitation. We don't get into that. There's a little bit of practice with it, but for the most part, we're just going to focus in on what gravity is and how we can measure mass and the force due to gravity, and also the acceleration due to gravity. We're going to be looking more at that than anything. Okay. Now, gravity acts on all objects with mass, and it also has an infinite range. So, and that is technically just the law of gravitation, universal gravitation, is that gravity acts as a field, and no matter where you're at in the universe, there is a measurable amount of gravity that's affecting you at any given moment. And that's what that means for the most part. Okay, now, we have to understand that have a better understanding what gravity is. So, because we all know gravity is what keeps us on Earth. And that's a great way to think of what gravity is. But a better image and a better idea of what gravity is we also have to understand why it is that we're, stuck on Earth. Why it is that we can't just jump up and then continually float off into space. And the reason why this is because what gravity actually is, what it's, a bit more closely, more specifically defined as, is the attraction between two large things. So here I've got a diagram, a picture of the sun and the earth and the moon. Okay. Now, gravity is the attraction of the earth here towards the sun. Okay. That's what gravity is. Gravity is also it's also the amount of attraction between the sun and the earth. Okay, because what we know is that the gravity is just how much force is seen between a number of objects based upon its mass and its distance. Okay, so gravity changes with how far away things are, and they change on how much mass one particular thing is compared to another. So fortunately for us, we are on Earth here, are at a very specific distance away from the sun here. And the Earth has a very particular mass, and the sun has a very particular mass. And also all the other planets within our solar system have a very particular distance and mass. That makes it super duper advantageous, like super duper advantageous. Not like a 1 in a million kind of odds here, but very, very not too far from it, that allows us to have an atmosphere that holds in gases, that holds in chemicals, holds in elements in order for us to live, to breathe, to thrive. Okay. So what does this have to do? What is the distance between the sun and the earth have to do with, the gravity that's experienced here on Earth? Well, again, there's an attractive force that's pulling these two things together. Okay. At the same time, there's also other planets that are attracted to one another. Okay. Celestial bodies that are attracted to one another at different angles, at different times, and all have different masses. And to put it into layman's terms, meaning into simpler terms, all those interactions together and attractions all produce more or less this force that happens to come down in every single direction towards the center of the Earth. Because again, we've got the sun that's massive, that's wanting to go this way, but we also have the Earth that wants to go this way. Okay, now you tell me what's bigger, the sun or the Earth? Clearly, the sun is greater than the Earth. The Earth also has a mass, and so those two ideas, the mass of the sun, the mass of the Earth, are going to both draw inward towards the Earth, which then produces our gravity. Okay. And again, it's based upon how far away these objects are from one another, and also the masses of them. Okay. Which is going to ultimately change this. It's going to change the gravitational force that's experienced on these planets. Okay. So here's like a pretty good idea of the difference between Earth and gravity. And I just noticed something that this image. So just so you know, kilograms, we measure kilograms in mass. This is a measurement of kilograms, not in mass. It's measurement in weight. Which, oh God. Oh my goodness. Just scribble this out, just so you don't get yourself confused in the future. Completely erase it. This is so stupid. I completely bungled that. Ignore that, because remember, mass is a measurement of how much matter a thing has in kilograms, whereas in weight is in pounds. We're going to see it in newtons, that sort of thing. It's also in kilograms, but that's different. At least in this kind of kilograms, that's different. Oh my goodness. Anyway, so based upon the mass of the Earth versus the mass of the sun, the distance that they have between them, we'll say that we have this amount of gravity that's pulling us down. Now, the moon happens to be way smaller than the Earth. It happens to be, relatively speaking, farther away. It's a bit, technically speaking, it's further away from the sun than the Earth is. So because of that, it has a very, very, but mainly to do with the fact of its mass, it has a super duper small amount of gravity. So if you are, say, 200 pounds on Earth, you're going to roughly weigh about 33.2 pounds on the moon. And that's due to the fact of the mass differences between the sun and the Earth and the moon, but also the distance between the sun and the Earth and the moon. Okay. Okay. I don't, what? Oh, no. That's weird. Okay. So hopefully we have a different understanding of how it is that gravity is measured, and and again, it's just how far masses are from each other in relationship to how much mass there is on those bodies. Now let's just talk about how it is that we can measure gravitational force as weight, and then we can also using a particular equation, and then where we can also calculate what the mass of a particular object is, and also what the acceleration due to gravity is on a particular planet. So we'll use F sub g in order to denote weight, or just force due to gravity. Weight we're going to be measuring in newtons. So anytime you're asked in a question, well, what's the weight of this object? It's asking you, what's the force due to gravity on this object? How many newtons does this weigh? Okay. Now, and I've already mentioned this, but we cannot get weight and mass confused because they're two separate things. And they both have something to do with these calculations. So remember, weight is a force on a mass, whereas a mass is a measurement of how much matter an object contains. Weight increases as mass increases, okay? But weight of an object can change depending on the gravitational force on an object. A person would weigh only about 1/6 as much as they do on the moon as they would on the Earth, okay? And again, you'll answer these on your own, and I'll answer these in a separate video. So because of this, because of the fact that there's a difference in mass and weight, okay, we have to know, and we have to know which one's which, because we're going to be using both in order to figure this stuff out. So gravitational force exerted on an object is the object's weight, and it's measured in newtons, and we use this formula in order to solve for it. So the force due to gravity is equal to the mass times the acceleration due to gravity. So again, F of g, force due to gravity, measured in newtons. The mass, oh boy, don't do that. The mass of an object is m. We measure that in units of kilograms. And then g is the acceleration due to gravity. And these are units in meters per second squared, which should make sense because it's acceleration. Now, so just keep this in mind. This is a resource for you to use when you're answering questions. If you're asked to find the force due to gravity or weight, your units are newtons. If you're asked to find the mass of an object, your units are kilograms. If you're asked to find the gravitation or the acceleration due to gravity, or g, your units are meters per second squared. Okay. So here are different ways that we can solve these variables, or solve for these variables using the weight equation. So here's basically what we did for same thing we did with speed, velocity, acceleration. But here, before you do that, get rid of this. I don't know how that 3 got in. You can scribble that out. It's g is equal to F sub g divided by m. There's no 3. Get rid of that 3. I don't know how that got in there. Scribble it out. Okay. So if you want to find the weight, you would use this equation. If you want to find the mass of an object, you would use this equation. If you want to find out what the acceleration due to gravity is, you would use this equation here. Okay. And then the last thing I'll leave you off with, I think it should be the last one, yeah. The last thing I'll leave you off with here, no, don't do that. Here, hold up. Last thing I'll leave you off with here on this long set of notes, thick set of notes. The acceleration due to gravity on Earth is 9.8 meters per second squared. Okay. So 9.8 meters per second squared is the acceleration due to gravity on average on Earth. Okay, it's more or less it's a universal constant almost anywhere you go on Earth. It does change when you go to the equator, and it does change when you go to the North or South Pole. But for the most part, it's a constant acceleration of 9.8 meters per second squared down towards the center of the Earth. So anyway, we'll be doing a lot of problems that have to do with weight, obviously on Earth. And so if you ever wonder what G is, this is what G is equal to on Earth. Okay, it's 9.8 meters per second squared. Okay. Again, I will have a separate video that will show you how to answer all the check your understandings. So I would go to that after you have finished up all the check your understandings. Other than that, guys, I know a longer video. It's a dense amount of notes, but realistically speaking, not too far off, not too different from things we've already talked about, things you've already seen. And yeah, we're just kind of taking a more mathematical look at most of these things and all that good stuff. So anyway, so that is a set of notes, guys. If you have any questions for me, make sure you ask those questions. If not, I will see you in the next one.